And if it rains.
Sports fans.
Yes, sir.
Okay, fellow Americans.
Fellow Americans.
So, 5 through 10 on the front kind of build off of each other, Mr. Reese. So if all goes well, when you get down to number 10, you should have an answer in the 500s. Right?
Number what?
On number 10, because it all builds off of each other. Your answer to number 10 should be in the 500s. Okay? Now, pay attention to number 1 and the fact that I've given you 3 significant digits on the one measurement that you need. Okay? So make sure your answer has 3 significant digits. If my Chem 1 students can get this concept, you guys can. I'm just saying.
Hey, wait. What about the number to 16?
Okay. Now, let's talk about number 16. Okay? So here's the deal on number 16. You got a hollow sphere spinning at 30 revolutions per minute, mass is 24 grams, radius is 3 centimeters. Determine the angular momentum. So, what 2 things do you need to calculate angular momentum?
IW.
Yeah. Moment of inertia and how fast it's spinning. So, you've got the moment of inertia, 2/3 mr squared. And then you've got the but the butt's in revolutions per minute, so you're going to have to change into radians per second. So if all goes well, your answer to number 16 should be a very small number, like something times 10 to the -5th. Okay? All right? So what that represents, and here's the big picture that you have to understand. What this represents is as that ball was spinning, that at that point is the total amount of angular momentum in the system. Okay? That's a fixed value. Boom. Okay? That's it. So unless we apply a large outside torque to either make it speed up or make it slow down, that value of L that you get is not going to change. Okay? That's it. Boom. Angular momentum has to be conserved. No variations on the theme. Boom. That's it. So here's what you want to look at. So along comes Bobby the bug, which looks like a rabbit, and he lands on the spinning ball at the equator. Okay?
So 16 and 17 go together? That's like 40. What's 17 approximately? That
Okay.
makes so much more sense.
Just, yes.
Let him get through it. He'll get there. Wow.
Yes, it's a continuation of the same problem.
Should have made a 16B on it.
Yeah, or like said using the information above.
Rate of spin. That's just...
Now, here's the big picture. Okay? Here is the ultimate big picture. So, this is a conservation of momentum problem. The only difference is it's an angular momentum problem. So here's what you've got. And this is how you're going to start 17. You're going to have L of the ball plus L of the bug is going to equal L prime of the ball plus L prime of the bug. Okay, that's it. Start with this. And this, the only difference would be, let's say for example, you had the ball traveling this way and you had the bug traveling in the opposite direction, not spinning. If all you had was linear momentum. If it was linear momentum, you'd go, oh, momentum of the ball plus momentum of the bug is going to equal new momentum of the ball plus new momentum of the bug. So the only difference is that if this one we're conserving angular momentum. On this one, we're conserving linear momentum. But it's the exact same conservation law. One's angular, one's linear. Now, let's say the bug, unfortunately, gets stuck and becomes part of the ball. So the bug's going this way, the ball's going this way, they hit. Bobby the bug meets an unfortunate end. He's now splattered all over the surface of the ball. So, because the ball and the bug are now one system, what can I do over here?
Add them together. Combine them. It's just the ball plus the full grams.
What? Somebody said it.
Factor.
Factor it out, right? So this would be the mass of the ball plus the mass of the bug times v prime. Okay? Boom. There you go. We're going to do the same thing up here with this angular momentum. What was the initial angular momentum of the bug? Zero. Okay, it wasn't part of the system. This had no angular momentum to start with. Boom, 0. So this is what you already found. You've already found this number. So this is something times 10 to the negative fifth kilogram meter squared per second. You know what this number is. So that means when I add these two numbers together, they have to add up to whatever you got here, because the momentum has to be conserved. Okay? Now, here's the deal. Are the ball and the bug going to spin at the same rate? Yes, because the bug lands on the spinning ball. Now, what you should see out of number 16 is that you're spinning at like 3.14 radians per second. That should be your omega on 16. So think this through. If you're spinning at 3.14 radians per second, and now the bug is part of the system, what do you know about your answer to 17 relative to that 3.14 radians per second? Bigger or smaller or the same? Smaller, because now the bug is contributing some moment of inertia to the system. Okay, it's contributing some of the I. So you know your answer to 17 has to be less than 3.14 radians per second. Okay, it has. Otherwise, you've created angular momentum, which would be cool, but it's a violation of, a pretty important conservation law, which is bad. So here's what you're going to do. Once you realize that that bug is part of the system, and I promise you, on the test tomorrow, there's going to be a problem like this. Make sure that you understand this. So over here, this is going to be the eye of the ball, okay? Kind of an eyeball thing. Plus a bug eye times butt prime. That's it. So the only thing you don't know is butt prime. You know everything else. Now, is the moment of the inertia of the ball going to change from what it was before the bug landed on it? Cheesehead number 3, Sam.
What?
Is the
Cheesehead number 3?
Yeah. They've all adopted this cheese thing. I don't know. So back row, I don't know. Back row cheeseheads, BRCs, back row cheeses. So
Sounds good.
yeah, BRCs, back row cheeses. So Mr. Cheesehead number 3, okay? When the ball lands on, when the bug lands on the ball, is that going to change the moment of inertia of the ball? Mr. Gilchrist.
Yes.
Wrong answer, play again.
Is the bug becoming a part of the ball? Is this when it's smacking into the ball, or is this in the problem?
This is in the problem. So
no, because it's separate mass.
yeah, so imagine here's the ball, right, that's spinning. What do you need to calculate the moment of inertia of this ball?
Mass and radius.
Mass and the radius. Mass of the ball, radius of the ball, right? Boom, that's all you need. So when the bug lands on the surface of this thing, that's not going to change the eyeball, okay? Because I still have the same mass of the ball. I still have the same radius. But what I do is I treat the bug as a point mass and use mr squared. Now, where's the bug going to be? Inside the ball or outside the ball? Yeah, so you just use this radius here as the same radius as you use for the eyeball, because the bug is landed on the outside of the ball. So whatever radius this is you have for this is the same one that you use there. So you already have this number. You've already calculated that moment of inertia in problem number 16. Now you just need to calculate the moment of inertia of the bug using mr squared. Add these two numbers together, divide over here, boom, there's your butt prime. Okay? So if all goes well on number 17, you should get an answer between 2 and 3 radians per second. If all goes well. Go with this. Yes?
On 18, to find the moment of inertia, is it just mr squared?
Yes, because you're just treating the moon as a point mass as it orbits around the Earth. Exactly. You're just going to use mr squared. You've got the mass, you've got the radius. Boom, there you go. So, now, your answer to 18 should be something times 10 to the 34th. It's a really, really big number. So, there's a couple of ways that you could spin, no pun intended, 18. So, one option is that you can find, at the end of the day, you need omega in radians per second, if you want to go that route. So, here's the deal, here's the moon. It's going to travel 1 revolution. 1 revolution is 2 pi radians. You take the days, change them into seconds, because this has to be in radians per second. Okay, and you're going to get this. You're going to use mr squared. You can then use L equals I omega. Okay? Boom. And then this I is going to be mr squared times what you get out of here. Boom, there you go. Okay? It's an option. If you want to do that, if you want to do like the substitution things that we worked through yesterday, where omega is 2 pi r over t, because that's fundamentally what it is, over r, you can do that as well. But anyway, you should get something times 10 to the 34th, which is a pretty big number. Okay? Good with that. Now, if you want to hold on to this, hand it in tomorrow, because the test is tomorrow, that's cool. If you're done with it, feeling good about it, whatever works for you. So, all right, so as you prepare for the test tomorrow, there's going to be 2 distinct parts of the test. Both of them, oddly enough, deal with momentum. One part of the test is going to deal with linear momentum, the other one's going to deal with angular momentum. Okay? Boom, there you have it. So let's kind of start at the beginning. How was lunch?
It was good on that.
I got in fast. I was actually on a physics field trip.
Where'd you go?
It's an exploration place.
Where'd you go for lunch?
You're going to stick with this story?
No, I just went to Pizza Hut.
Okay.
Kendra's not here though, so.
No excuses.
It's time to get out.
But
Just say, hey, Burkamp, you bought soup for me yesterday. Maybe I can.
I forgot about that.
Yeah. You have to cancel your order and go.
No, you can't do it. You can't do it.
Cancel that order.
Okay.
I'll take 20% off your order.
So,
I already got some checks. So.
let's say that you have a block
At least you're honest.
moving a certain velocity, I don't know, 5 meters per second. Okay? And it's going to hit another one. So what could possibly happen during this collision? They could stick together and move off, right? So here's block A, here's block B. How does every momentum problem start?
Without
What'd you say, Ms. Treadway?
nothing else mattering.
I know you were.
I don't. What if I'm wrong? You're gonna say.
Last time you lost.
Because if you gave me a wrong answer, that would be the first time in 27 years of teaching that a student has ever given me a wrong answer.
Pretty
Probably.
impressive.
Is it the PA plus B?
Beautiful.
Okay.
So you're going to start momentum of A plus momentum of B equals new momentum of A plus new momentum of B. Okay? Boom. There you go. So, if they move off together, what can you do on this side? Factor out? Yeah. So if they move off together, you can go mass of A plus mass of B times B prime. Only if they move off together. So another option is that they hit and they bounce in opposite directions. Okay, maybe there's a spring involved. So if you're not told that they move off together, then you have to figure out these momentums separately. Now, block A hits block B. Does block A exert a force on block B? Yes!
Obviously.
Dear Lord!
That's the source of the force.
Too simple.
Okay, so block A exerts a force on B. Does B exert a force on A? Yes, and the magnitudes of the forces are equal and opposite. Do not make this complicated. Tomorrow, if I ask you, hey, something hits something, what do you know about the magnitude of the forces? They're equal and opposite. Don't screw it up, okay? There's nothing to think about. Is the momentum of block A going to change? When it collides with B, is the momentum going to change?
Yeah.
Yes. So what do you know about the change in momentum of A relative to the change in momentum of B?
Equal.
Yeah, they're going to be equal and opposite, because whatever momentum is lost by A has to be gained by
B.
B. Okay? Now, is it possible, okay, think this through. Is it possible for block A to hit block B and they just stop?
No, A's gonna have to bounce back.
No.
No, that'd be dumb.
No.
Because then there would be no momentum.
Well, didn't that happen on your swinging thing? Didn't they just hit it and
Not like people think.
kind of stop?
But it moved back, the block moved.
Yeah, no, it's impossible.
Yeah, because look, if this side has any value at all for momentum, which it does because block A is moving, then there's no way after the collision that everything just stops. Okay? It can't go along, hit this, boom, and it just comes to a dead stop. There has to be some momentum over here if there's some momentum over there. Now, if they do come to a stop, what is the only way that this side of the equation over here could equal 0?
The other side did.
If they didn't weigh anything.
Everything's gotta weigh something.
What's the only way these two values can add up to 0?
They're opposite.
And the same value. So this could be -4 and +4. So this side could add up equal to 0 as long as these momentums are
0 to equal to 0.
R
equal
zero.
and opposite so that they add up to equal to 0. If one of these is bigger than the other one, then it's got to keep going. Okay. So we got that one. On a fourth time graph. So let's say that I give you a fourth time graph that looks like this. What can, and let's say this is 10 newtons. And let's say this is 6 seconds. So that's your force time graph. So what can you determine from that force time graph?
Well, it's slowing down.
Its momentum is going down.
No.
Okay? Hold on.
That was velocity.
It's a force time graph. Oh, the area is going to equal the
Good answer.
change in momentum, right? Now, am I applying a constant force the entire time? No. Okay? What's actually happening to the force? It's becoming smaller. So this could be a situation where it's a rocket engine that has run out of fuel and it's supplying less and less and less force until it doesn't supply any force at all. Okay? Or your engine on your car has run out of fuel. Okay? And you're applying less and less force until there is no force left to apply. So Elliot is right. You got a triangle. You got 10 times 6 gets you 60. Half of 60 is 30. So this area of 30 Newton seconds represents your change in momentum. Now, is that enough information to find the change in velocity of the object? Neat.
Yeah.
It is. I can find the change in velocity from that number.
I think you had a question earlier, but yeah.
He was just saying yes or
I was
something.
like, yeah, what's the question, Bert? Those, yeah.
So you want to stick with yes now that you know what the question is?
No, let me think about it real quick.
Okay, so
Consult your fellow Cheez-Its.
what you say, you trying to determine the change in.
I'm trying to find the change in velocity. That's what I'm trying to find. Is that enough information to find the change in the velocity of the object?
No.
Why not?
You need math.
I need math.
Oh, yeah.
Because if I apply, if this is my change in my momentum, right? If this is my change in my momentum. So, if this is my change in my momentum, then change in momentum also equals what?
Mass
Force times time, which we just did, but it also equals
mass v.
mass delta V.
Yep.
So, if I apply this diminishing force to an aircraft carrier versus applying this diminishing force to a toothpick, they're going to have vastly different changes in velocity. So that's why mass has to be a factor. So if the mass is 1 kilogram, then what's my change in my velocity?
I'm going to take 30 divided by 1.
Maybe 30?
That's what I'm thinking.
Yeah.
30.
Now, the change in my velocity is 30. Does that mean that I'm going from 0 to 30 meters per second?
Not necessarily.
Not necessarily.
Good.
That's just by changing my velocity. I could be going from 5 to 35. I could be going from 5, 10 to 40. It doesn't make any difference. All I know is that's my change in my velocity. Okay? That's all I know. That's just my change in my velocity. Now, if the mass is bigger, let's say that that's a 2 kilogram mass, then what's going to be my change in my velocity? Then it's going to be 15. So as the mass gets bigger, the change in velocity becomes smaller. Okay? If the same force is applied over the same time. Now, what if I applied a constant force of 10 newtons for 6 seconds? Now what's going to happen to my change in my momentum? Brooklyn. What's going to happen to my change in my momentum if I apply a constant force of 10 newtons for 6 seconds? What's it going to do? Increase or decrease? What's it going to be? What's the numeric value for the change in my momentum? 60. 10 times 6, boom, I get 60. So if I apply a constant force of 10 newtons over 6 seconds, I get a change in momentum of 60. Okay? And if you think about it, that should make sense because I'm applying that 10 Newton force over this entire interval. So that's like holding your gas pedal down at a constant rate for 6 seconds as opposed to running out of gas and diminishing the smaller force. So with a bigger area on a force time graph, that's going to create a larger change in momentum. Okay? Now, here's what you have to be careful of. This is what you have to watch. Because there's so many things that can be equal, force times time, change in momentum, mass, delta V, and change in momentum also equals P, momentum minus, momentum final minus momentum initial, okay? You have to pay attention to what you're holding constant and what you're changing, okay? So let's say, for example, you're in your car and you're going to go from 0 to 20 miles per hour in 2 seconds. Is your momentum going to change? Yeah. Okay? Right? You're going to go from 0 to 20, 2 seconds. Your momentum is going to change. That's going to require a certain amount of force, right? Now, if you go from 0 to 20 in 15 seconds, what's going to happen to your change in momentum?
What was the first one?
Did you say the time increases, it's going to be bigger, so it changes bigger?
Okay, let's look at this. So you have two situations. Here's the car, right? I'm going to go from 0 to 20. In this situation, I'm going to do it in, say, realistically, 2 seconds. Okay, you've got a really hopped up car. Okay?
What does that say?
Dude, 0 to 20 meters or something.
What was that?
You do this.
20 miles per hour. Better? Now, situation number 2, I'm going to go from 0 to 20 miles per hour, but that's going to take me 15 seconds. In which situation does the car undergo a greater change in momentum? Situation number 1, situation number 2.
Neither.
Or neither.
Neither.
Neither. Why is the change in momentum the same? It's the same change in velocity at the same mass, right? Now, which one will require more force? The first one will, because you're going to undergo that change in momentum in a much smaller time. So on a force time graph, right, this one's going to be a large force over a short period of time. This one's going to be a smaller force over a longer period of time. But the areas are going to be the same. Okay? Makes sense. Now, if I apply the same force for a longer period of time, then what's going to happen to the change in momentum? Then it will, what'd you say, Ellie?
Go up.
Then it'll go up. So if I apply a big force over a long period of time, that's going to create a huge change in momentum. Okay? So you have to focus on what you're holding constant. Are you holding force constant? Are you holding time constant? Change in velocity? What are you going to hold constant? Okay? All right.
This is just kind of like our review.
Kind of. Okay. So let's say that I take yonder tennis ball. Yonder tennis ball.
What's that? What is y'all doing now?
What?
Those two mixtures.
It's just a
Plutonium
concentrated
and
in diluted solution of nitrate.
Plutonium and uranium.
Okay, so I'll take the tennis ball, right?
Oh, it dropped the
Why
mass.
would you do that?
No. Don't look at me. I was trying to help and save it.
Okay, so I'm going to give this thing a roll, and then oddly enough, it comes to a inclinatio ad quitter. So let's say the ball rolls a certain distance.
17 meters.
How about point? Okay, we're 17. Yeah. So Did the ball undergo linear acceleration from the point that I let go of it?
Yes.
Yes.
Yes, why? Hunter?
Stop.
I mean, it's gonna have to take some sort of time, to get to where it was.
Did it slow down?
No, it sped up.
Okay, from the time that from the point that I let go of it.
Yeah, slow down.
Slow
You got
down.
force acting on it.
Yeah?
Friction.
Little friction, right? So, here's the point. Let's say that it's initially moving at 2 meters per second. Okay?
I don't know, mine was just.
And it stopped in 0.3 meters. Could I find the linear acceleration?
Yeah.
Yeah. You know the initial velocity? Do you know the final velocity? Do you know the distance? Yeah. Guess what you could use? That equation. Okay? Let's say that the radius of the ball is 0.05 meters. Does it also have an angular velocity?
Yeah.
Yes, because it was rolling, right?
Ooh.
So you know V equals
R omega.
R omega, right? So do you know the linear velocity?
Yes.
Yes. Do you know the radius?
Yes.
You could find
Omega.
omega.
Now, how would you do that since it's not constant?
No. This is at this point. This is what it would be.
What do you mean?
Okay, you're starting at 2 meters per second. So
Right.
you would have your initial angular velocity just like you have an initial linear velocity. Okay?
So we're not trying to find the theta, is that what it's called?
Oh, I could.
How would you do that since
Well,
it's
let's try.
Stop getting ahead, Hunter.
Okay? So here's my question. Can I find omega? Yeah, so let's do this. So let's take 2 meters per second and divide that by 0.05 meters. What units am I going to end up in?
Meters per
Wrong!
Radians per second.
Radius.
Radians per second. Meters cancel out, the radians float back in. So take 2 and divide it by 0.05. You should get 40.
40.
Okay?
Just heads up math.
40 radians per second. Now, is it going to stop? Is it going to undergo angular acceleration? Yes.
Yeah.
Yeah? So you can sit here and go, oh, omega squared equals omega naught squared plus 2 alpha theta. So here's the deal. You know your initial, you know your final. But here's what you don't know, is that you don't know alpha. But do you have it? Could you find alpha if you know your linear acceleration?
Yeah.
How do you do that?
A.
You know the initial linear velocity, 2.
Oh, no, the end is 0.
That's 0. You know the distance that it travels,
0.3. You don't know that.
but you can find it.
Okay, so we're going to find our acceleration.
You can find your linear acceleration.
Okay, so how do you convert those?
Then
Oh, you just divide by a radius,
A
right?
equals R alpha.
Okay,
A equals R alpha.
so you would just divide by the radius.
Yeah. So once you get this from this equation, divide that by the radius, there's alpha, bam, slam that in there.
Slam dunk.
Oh! I just had such bad chills.
I wish I could save that.
Okay.
Buddy, how are you today? You've been quiet. We don't have Kendra back there.
I know, it's pretty
Let's,
lonely.
okay. So there's, like I said, here's the certain problems I promise you will be on there. Bug landing on a ball. Promise you it's going to be there. Okay? Promise you it's going to be there. The ball being dropped, hitting the floor, and bouncing.
Can we do that
Promise
one?
you.
Can we do one of those?
He asked
There's
nicely.
one on the review.
That one.
Or I can work one now.
No, just do it on the review. It's on the review.
It's on the review.
Let's just do that.
Those ones take like an hour to
That one was
do.
Yeah,
That one's probably gonna be worth like 30 points.
yeah.
Probably like 3 points.
But guess what? You know it's going to be on the
That
test.
doesn't mean I can do it. Doesn't mean I know how to do it.
Hey,
This is
Look.
the problem.
Mr. Taylor, you've played sports,
He is a sports player.
okay? Played basketball?
Oh, he's a heck
Okay.
of a basketball player.
When you started to play basketball, could you dribble very well?
No.
What did you do to get better?
Practice.
Practice. So you're going to have this ball drop problem. You go, wow, I'm not very good at it. Guess what? Work it again and again
There's not
and
enough
again.
time in the world to practice ball drop problems.
Okay?
Tell him. No.
But if you look at that ball drop problem from a big picture standpoint, that's the thing. Don't memorize the steps. Look at the big picture. Now, on the ball drop problem, listen to me. I'm going to lay this out in the instructions on the test. You pay attention to every sign on the displacement, on the velocity, on the acceleration. Okay? Leave nothing to chance. You make sure.
What that literally had nothing to do with that thing. Just go. That you didn't have to move that. I wasn't.
Yeah, okay.
I promise you that. Nothing.
All right. Anyway, so make sure that when you're working that problem, you pay attention to the signs. Do not randomly write down numbers and then, oh, a miracle happened and it became negative. Okay?
Like the radius.
Well, that's kind of a miracle. Okay. All right.
Oh, dude.
Anyway,
Funny.
let me pose this
Why are you
question.
laughing?
Let me pose
it's
this
so
question.
funny. Are we doing it?
No, I'm just posing this question.
Ball dropping off the table.
You're really good at drawing.
We're going back to the,
I know, honestly.
Were you in art class in high school?
No, he's been in physics more than we've been alive. There's a reason he can draw these problems well.
were you saying about every test this person?
Got me on that one. Oh, small fish, big eyes. Big eyes, small fish.
Okay, so visualize this situation. I have a small cart hooked up to a weight on the end of a string. I have a much larger cart, same weight, hooked up to the string. Okay? I start the watch, and this thing, both are pulled for like 1 second. Okay? So this gets pulled for 1 second. This thing gets pulled for 1 second. Okay? Which one will undergo the greatest change in momentum? Large cart? Small cart? Or is it the same change in momentum?
Figure math.
Oh.
I'm scared. I'm scared.
She's at number 2.
Joseph, that's you're number 2. No.
Joseph, she's at number 1.
Joseph, you just
You said the masses are the same, right?
These masses on the end are the same.
Can you do the big one?
Why?
You guys have more force.
Why?
No. The force that's applied here is the same because it's the same weight. Like this might be like 0.2 kilograms. So I'm applying the same force to each one of them. I'm applying the same force for the same amount of time.
Oh yeah, it's the same. Just
Yeah, they're both going to undergo the same change in momentum. Why? Because force times time equals change in momentum. Which one's going to be going faster? The smaller car is because of the fact that it has a smaller mass, so to create the same change in momentum, it has to be going faster. Now, you can also look at this in terms of F equals ma. You have the same force, right? With the same force, the one that has a smaller mass will end up with a larger acceleration. Larger acceleration at the same time, I get a higher velocity. Okay?
Got it.
Now,
In theory.
let's say I took it yonder bicycle wheel.
You and this word.
Huh?
You and this word yonder.
I like the word yonder.
What does it define it?
What do you mean yonder? It's like over,
I thought it was
beyond.
this.
So how does that apply to that?
It's a yonder wheel.
Mix those.
Over their wheel?
Yeah, how
Yes.
does yonder make any sense?
Oh, just shut up! Hey!
I'm just
It
wondering.
literally doesn't.
Okay,
That's like the handles are
Now-
irrelevant.
here's the
Yeah,
deal.
exactly, that's what I'm.
What is going to determine the acceleration of this wheel? What are some factors that will determine the angular acceleration of this wheel? Do you mind?
I told you to.
What will determine the angular acceleration of this wheel? Name one thing.
No,
The radius.
Yes.
What about the radius? The radius of what? The radius of the wheel? Or the radius of where I apply a
Yeah,
force?
there is reapply the force.
The radius of where I apply the force.
That's torque, right?
Okay? Because remember, torque equals two things. What does torque equal? Fr and it equals
I fish. I fish.
I fish, right? So, when you're talking about the radius, you have to be careful about which radius you're talking about. So if I apply the same force here, and I apply the same force out there, am I going to get the same acceleration?
No.
No. This is why you can't use F equals ma on spinning object. Because if you apply the same force, you're going to get completely different angular accelerations. So the radius of where I apply the force is going to be a factor. What else is going to be a factor? Well, we talked about this radius. Perhaps the amount of force that I apply? I think that would seem reasonable. So if I apply just a little bit of force, I get just a little bit of acceleration. If I apply a lot of force, I get a lot of acceleration. Okay? So the amount of force that I apply and the radius, where I apply the force. Right? Now, is there a radius implied in this moment of inertia? Yes. So what's the other radius that will impact this deal?
The radius of the tire.
What'd you say?
The radius of the tire.
Yeah. So if I've got a really, if I shrink this tire down like this, okay, what's going to happen in my moment of inertia?
It's gonna decrease.
It'll decrease. So not only is the radius about where I apply the force, it's also about the radius of the tire itself. Okay? Because that's going to determine the moment of inertia. Now, listen to me. When you look at that mr squared, it's a general equation. But in terms of actually calculating moment of inertia, you can only do that in two distinct situations. When it is a
Point mass.
or a thin hoop. Anything else, you cannot use mr squared. Solid disk, hollow sphere, solid sphere, door, whatever it is. Okay? So be careful about that idea of mr squared. But what units is every moment of inertia measured in?
Kilogram meter square.
What units is every moment of inertia measured in? Kilogram meter squared. No matter how you calculate it, it's always kilograms meter squared.
Are
Okay?
you gonna give us these equations?
They're on your equation sheet on the back side.
Oh, okay, thank you. I see it.
Yeah, they're there. You've got it. Okay, I am done.